Hello everyone from Math 2000, Linear Algebra. It's Professor Wenson here again with a video on your ZyBooks Section 3.3 titled The Dot Product. Alright, so this is going to be another operation that we're going to perform with vectors. The only main difference is, instead of, remember scalar multiplication of a vector and it ended up with another vector. When you added two vectors, that resulted in another vector. This thing called the dot product of two vectors is not going to result in another vector. It will simply result in a scalar, or just a real number. And we'll see all that coming up. Alright, so I'll leave the summary for you to read. You got the 5 objectives here. Let's just start with the dot product. Right, the dot product of two vectors u and v, denoted by u dot v. So I might just say dot a lot. So u dot v is the sum of the products of the corresponding components. So another way to put this, they do it symbolically here. So suppose u is the vector with these n components, u1 through un, and v is the vector with these n components as well, v1 through vn. Notice how they have the same number of components. If they don't have the same number of components, then the dot product will not be defined. Then here's a little formula for how do you find this dot product. U dot v is the sum, right? Anytime you see this sigma notation, it's a summation from I equals 1 to n of ui times vi, meaning, starting with 1, u1 times v1 plus u2 times v2 plus, u3 times v3 plus, all the way to, the product of the last components, un times vn. So again, pretty simple arithmetic here. You're just multiplying the corresponding components and then adding those products up. So notice, the result is a number. Right? This result is a number, not a vector. So that's what they're saying here. While vector addition and subtraction are operations that produce another vector, the dot product produces a scalar, and I'll highlight this. Please remember this. The dot product produces a scalar, a number. Also, the dot product is only defined for two vectors with the same number of components, as I mentioned earlier. Alright, so if you have one vector with 3 components and another vector with 5 components, then the dot product u dot v is undefined. Okay, so I'll write this out on some paper here. Very simple to do, pretty easy arithmetic I feel, but I'll show you a couple dot products. Alright, so here's the first dot product in the example in the book there, example 331. And you see the dot symbol, right? So here's a vector from R3, right? A vector with 3 real number components. And it's being dotted with another vector with 3 components, right? And again, they have to have the same number of components. So again, very simple arithmetic I feel. You're just taking the sum of the products of the corresponding components. Right? So the product of the first components, so 5 times 1, plus the product of the second components, 0 times negative 3, plus the product of the third components, negative 2 times positive 4. So we have here 5 plus 0 and then minus 8, right? Plus negative 8. So this all ends up resulting in negative 3. But notice again that it ends up being a scalar. right? Just a real number, not another vector. Okay? And it really is as simple as that. Just the sum of the products of corresponding components. All right, so now I'll just, you can read example B here. You have a vector with 5 components, dot product with another vector with 5 components. All right, so you're multiplying the first components plus the product of the second components plus, all the way up to the product of the 5th components, and then adding those numbers up. And then example C, see, I have a vector from R2. I have a vector with 2 components dotted with a vector from R4, a vector with 4 components. This cannot be done. The dot product is not defined when the two vectors have different numbers of components. All right, so you see here, part C, the dot product is undefined. All right, so again, very simple these. Here, you're doing the dot product. I'll just do this first one, leave the others to you. And if it's undefined, you just type the word undefined in the space provided. So here's a vector with 2 components, dot product with a vector with 2 components. So they've got the same numbers of components. The dot product will be defined. And it's the product of the first components. -3 times -1 is +3, plus the product of the second components. 7 times 5 is 35. 3 plus 35 is, positive 38. Right? So I'm entering 38 there and checking. Great, it's correct. Then again, you have 5 components, dot product with a vector with 5 components. So the dot product exists, it's defined, you can find it. And then just type undefined for this last one because it's 3 components with a vector with 4 components. The dot product is not defined. All right, then here, start challenge activity. Again, it's just finding dot products. And there's only 3 of these. These are pretty simple, as you've seen. 0 times -8 is 0. 9 times -3 is -27. 0 plus -27 is -27. And then I move on to the next level. Right, and then it's dot product of 2 vectors of 3 components. Again, very, very simple arithmetic. Now, what does the dot product help us determine? All right, you might have asked that in the beginning. Why are we doing this? Right? What's the point of multiplying these corresponding components and adding them up? Well, what you're going to see in here, the second part, the geometric interpretation of the dot product. Well, we're going to be introduced to another formula for the dot product. Okay, so please memorize this, and I'll write it down, of course, when I go over some examples. But in R2 and R3, right, so 2-dimensional space and 3-dimensional space, the dot product can also be expressed in terms of the vector's magnitudes and the cosine of the angle between the vectors. Now this formula also applies to higher dimensional spaces, not just R2 and R3. It's just in R2 and R3, it's easier to visualize, what vectors look like and what's the angle between them. So you got a couple pictures down here. And here's, again, I highly recommend you memorize this to make your exercises very quick and easy. So another way to calculate the dot product, and we'll see, and you can actually see that these are the same these will end up giving you the same values. U dot V is equivalent to the magnitude or length of vector U times the magnitude or length of vector V times the cosine of theta, where theta is the angle formed by the two vectors. And I'll say it's an angle, the angle formed that's from 0 degrees to 180 degrees. All right, that's this because technically every pair of vectors, if you look at the picture here, see there's a large angle, right? Something called a reflex angle, the large angle that the two vectors form. We're talking, when we say theta here, we're talking, the smaller of the two angles formed. Again, here's in 3 dimensions, two vectors. Again, you see there's a large angle if I wrap around this way, but we're talking the smaller angle formed between them. All right, so this angle measure theta is going to range from 0 degrees to 180 degrees, or from 0 radians to 180 radians. All right. Okay. So let's take a look at so what we're going to be able. All right. So the point of this section, this part of the section, is we're going to be able to use the dot product that we found up here. Right. We're going to be able to use the dot product of two vectors, and we'll be able to find the measure of the angle they form. Right. If you were to draw both the vectors in standard position, starting from the origin, and you say, hey, what's the angle they form? That we can find that now using the dot product and the magnitudes. All right, and I'll show you some examples of that. All right, so first, this example here I'll take to some paper. Okay, so here are the two vectors given in example 332, the first part A. I have vector A has components, 2, 5, and this is in R2, right, two-dimensional space. They're drawn here with two axes, the x1 axis, x2 axis, or the x-axis, y-axis. Vector B has these two components, negative 1, 3. And what I've done here is I've drawn these two vectors in standard position, right, starting from the origin. So this vector is, go to the right 2, up 5, so that motion there. This vector is left 1, up 3, that motion there. And what I'm going to use that formula that was mentioned earlier, and I'll write it down, of course. We're going to find this angle right here. What's the angle formed? Right, I'll call this theta. Now again, like I said earlier, there's a larger angle formed, right? But we're talking about an angle between 0 and 180 degrees. Right? We can find the measure of this angle. Now, looking at this picture, this definitely looks like, some acute angle measure. So hopefully when I'm done going through this, we'll see that theta is between 0 and 90 degrees, right? Some acute angle measure. All right, so here is that formula mentioned. The dot product of two vectors. All right, the dot product of two vectors is equivalent to the magnitude of the first vector multiplied by the magnitude of the second vector multiplied by the cosine of the angle between them. Right, so this theta here is this theta here. All right, and I know all the information here except for theta, right? Because we can find the magnitude of A. Right? Remember the length of a vector in R2, R3, R whatever was pretty easy to find. It was just the square root of the sum of the squares of the components, right? So 2 squared plus 5 squared. So this is the square root of 29, right? 4 plus 25. And the same thing goes, I can easily find the magnitude of vector B. It's the length of it, the square root of, negative 1 squared plus 3 squared. That's the square root of 10, right? And the dot product, right? We know the dot product as well, right, from earlier. That's just the sum of the products of their corresponding components. The dot product, right, the left side of this formula is going to be this number, 2 times negative 1, right, the product of the first components, plus, and then 5 times 3. That's negative 2 plus 15. It's positive 13. So I know the left side. I can fill in the magnitude of A, right? This is square root of 29. I can fill in the magnitude of B. That's the square root of 10. So the only thing I'll be missing is the value of theta, and that's what we're going to solve for. So I'll put this in a box. This is, again, I'll put a star next to it. I recommend you memorize this. So we have 13 for the dot product is equal to the square root of 29 times the square root of 10 times the cosine of theta. And then I'm going to solve this for theta. So in order to do that, we got to get rid of these numbers. That'll involve division. Right, so we'll have the cosine of theta alone equals 13 divided by, now the square root of 29 times the square root of 10 here, I can make that the square root of 290. Right, 29 times 10, they're both inside square roots, and they're square roots of positive numbers, so I can do that. Right? And then to solve for theta would require, taking the inverse cosine of both sides. So we're seeing theta equals, the inverse cosine. That was that cosine with a negative 1 above it, or arc cosine of this number of 13 divided by the square root of 290. Alright, so let's see what this is. I'm going to put this in degrees. Right, we're in the book here, you're going to notice they're going to ask for a lot of things in degrees. So I'll pull a calculator up. Now I've got a TI-84 plus. Right, you've seen this before. 84 plus, TI-83, 84 all work pretty similarly. Alright, so let's turn it on here, and then make sure, since I want my answer in degrees, click on mode here. You see right now it's in radian mode. I want it so that my angle measures are in degrees, so I'm going to click on degree there. Alright, and then I'll enter this inverse cosine. Now that's above the cosine button. You go second cosine, you see the little cosine negative 1 there, that's a inverse cosine. And then inside I have 13 divided by the square root of 29 times 10, right? It was the square root of 29 times 10. So this is the square root of 290. And then close parentheses, and here we're getting approximately 40.27 if I go to the nearest hundredth. I don't know. Depends on what they ask me for. Degrees. Alright, so almost 40 degrees, a little over 40 degrees. Alright, so I'll say this is approximately a 40-degree angle here formed by the two vectors. Alright, just a little more than 40 degrees. Great. Okay, and this is what this part of the section is about. Alright, using the dot product of two vectors and the magnitudes or the lengths of those vectors to also find the angle between them, the angle that they form. Okay, wonderful. All right, so I'll do the next one as well. All right, so I'll pull these two vectors up, vectors m and n here, and work on it on some paper. All right, so here we have from the same example vectors from R3, right? Vectors with 3 components. M is 0, negative 4, 1. N is 6, negative 1, 1. And I tried my best here to draw a picture of this where you have the x1 axis coming out of the page, and then the x2 and x3 axis are on the page. And here's vector m, here's vector n. And what we're trying to figure out here is what's this angle between them. This is theta here, right? This angle between them. Again, now being that they're in 3 dimensions, hard to tell on a piece of paper, but it does seem to me that this looks like another acute angle. Now, vector m could be pointing back here, but I know that vector m is actually on the x2, x3 plane because x1 is 0. And so it's not going pointing back, it's pointing like, it's like, imagine this is on the paper and this is coming out at this angle here. So it looks like this is an acute angle, but we'll see. We'll actually figure this out. Alright, so I've got vectors m and n. Let's find their magnitudes. How long are they? So what's the magnitude of vector m? Remember, very easy formula. It's the square root of 0 plus 16 plus 1. So the square root of 17. Alright, the square root of the sum of the squares of the components. And then the norm, sorry, I keep saying norm in these videos. You'll see the word norm come up later. The magnitude of vector n, the length of vector n, is the square root of 36 plus 1 plus 1. So the square root of 38. All right, and then the dot product, m dot n, would be, again, the sum of the products of the corresponding components. So 0 plus 4 plus 1, which would be 5. And then I'll write this formula again, involving the dot product, the magnitudes, and the angle between the vectors, the angle the vectors form. So m dot n should be equivalent to the magnitude of m times the magnitude of n times the cosine of the angle between them, the cosine of theta, and we'll solve for theta. Alright, so m dot n is 5. We saw that. The dot product is 5. The norm, I keep saying norm. The magnitude of m is the square root of 17. The magnitude of n is the square root of 38. And then times the cosine of theta. Now hopefully you can see here that theta will end up being the inverse cosine of, the dot product, 5, divided by the product of the magnitudes, right? The square root of, I'm just going to enter it this way in the calculator. Whatever 17 times 38 is, you have the square root of that. Okay. So we'll have theta is approximately, whatever this number is. Now that's not 17.38, right? That's 17 times 38. So on the calculator, inverse cosine of 5 divided by, and then in the denominator, the square root of 17 times 38. And again, make sure all of that is inside the square root, right? They're both inside square roots there. So yeah, it is an acute angle. This is approximately 79 degrees, 78.65 degrees. Right? And again, I'm still in degree mode. So there's the angle between them, the angle formed by these two vectors in R3. Okay. Now let me give you a little tip. And this isn't pointed out in the ZyBooks. This is just something I'm going to mention. Did you notice how the dot product of the vectors was positive here, and the angle between them was acute? And then even in the last example, the dot product of the two vectors was a positive number, and the angle between them was acute. Okay. That will always happen. So let me get rid of the calculator. So in general, if the dot product of two vectors, say, the vector u and v, if it's a positive number, then again that theta right? Theta represented the angle between them, is acute. It will be acute, meaning that it's between, maybe including 0, but less than 90. Okay. If the dot product, and we haven't seen an example of this yet, but you will when you work on other problems, if the dot product is negative, right, less than 0, then the angle between the vectors will be obtuse, meaning that it's bigger than 90 degrees, but not equal, right? Bigger than 90 degrees, up to and possibly including 180 degrees. And then this is actually mentioned in the book here, this third one, and I'll put a little star next to it because this is important. This third concept comes up a lot. If the dot product of two vectors is equal to 0, then theta is a right angle, is equal to 90 degrees. The two vectors are going to be forming a right angle. And when this happens, right, if the dot product of two vectors is 0, if two vectors form a 90-degree angle when you put them in standard position, they call those kinds of vectors orthogonal vectors. They're orthogonal to one another. Another fancy, kind of a fancy way of saying perpendicular. And that's actually mentioned here. So you can read through these examples. We found these angles and junk. And I'll leave the participation activity to you. So do the same thing. What would be the find the angle formed in degrees between vectors f and g here in R2 and between vectors a and b in R3. Now notice how they want you to type them. It says type as, and then see it's number, point, number, number. Number, point, number, number. So it looks like they want you to round to the nearest hundredth, right? 2 decimal places like I was doing, and enter your answer to the nearest 2 decimal places, the nearest hundredth in your spaces. So I'll leave those to you. Now I just mentioned this word, right? Two vectors are orthogonal. Very important word. In fact, later in chapter 9 of the book, you're probably going to get sick of hearing the word orthogonal. But two vectors are orthogonal if the angle between the two vectors is 90 degrees. All right, so the geometric definition of the dot product can be used to determine whether two vectors are orthogonal. Since theta equals 90 degrees is the only angle from 0 to 180 for which the cosine of theta is 0. Right? Remember that formula had the cosine of theta in it. The only time the cosine is 0 in this interval is when theta is 90 degrees. So huge theorem right here. Two vectors are orthogonal if and only if, right? This is a biconditional. This is going in both directions. The dot product of the vectors is 0. Okay. All right. So they ask to determine whether the pair of vectors are orthogonal. Just take the dot product. There'd be 4 plus 0 plus 0. The dot product of these first two vectors is positive 4. These are not orthogonal. And as I mentioned earlier, the dot product of these two vectors is positive. So the angle between them will be an acute angle, right? Less than 90 degrees. For number 2, you have 2 times 6 plus negative 3 times 4. That's 12 plus negative 12. That is 0. These are orthogonal. They would, if you drew them out in standard position, they would form a 90-degree angle. And I'll leave that to you to draw. Alright, so again, just looking at these, very simple. 12 minus 12 is 0, so these are orthogonal. Now here's a key point to make. If one of the vectors is the 0 vector, right, vector with all 0 components, then it doesn't matter what the other vector is. As long as it has the same number of components, they'll be orthogonal. The 0 vector is orthogonal to any other vector because their dot product will be 0. And I'll leave the last one to you. Alright, so this one, I'll pull the calculator up. So it's asking us to find the angle theta in degrees between u and v, and then careful, look at the example inside the block there. See, it wants you to enter a number, point, and then 3 numbers this time. So enter to the nearest thousandth, not the nearest hundredth, like this activity here. So this one looks like they're wanting me to enter to the nearest thousandth. So I hit start. Now remember, I'm just going to enter that inverse cosine right now because I know the structure. So I'd be taking the inverse cosine, right, to find the angle between these vectors. And then inside the inverse cosine, right, the numerator is the dot product. Well, the dot product of these two vectors is 40, right, 40 plus 0. So inside this inverse cosine, the numerator is going to be 40 divided by, and then the square root of, now the magnitude of this vector is just, 5, but like I'd be taking the square root of 25, so like, the first number I'll put down here is 25 times, and then when I try to find the magnitude of v, it'd be the square root of 64 plus 25, which is 89. So I'd have the square root of 25 times the square root of 89. Right, so that's why I got 25 times 89 down there inside the square root. And this is approximately 32.005 degrees, right? Again, look at the way it's entered. They want to the nearest thousandth of a degree. So the angle between these two vectors is 32.005 when rounded to the nearest thousandth degrees. I check, see that is correct. And there are 4 of these. I don't know if every single one of them is finding an angle. Looks like this one is as well. And so again, I'll leave this one to you. And again, pay attention. They want three decimal places. All right, so nearest thousandth of a degree. And make sure your calculator is in degree mode. Okay. Then some properties of the dot product. There's just a few here. Again, hopefully these are pretty obvious. I'm not going to go in through the proofs or anything. I'll just read them off. The dot product is commutative, right? Meaning that you can do it in either order and get the same result. U dot v will be exactly the same as v dot u. The dot product is distributive over vector addition. Right? You can distribute a dot product over vector addition or subtraction. So u dot the quantity v plus w would be exactly the same as u dot v plus u dot w. And finally here it's associative over scalar multiplication. So that means if you have a scalar, so this little c here, notice how it's not bold. This little c is a scalar, a real number. If you have a number times a dot product, you can, if you like, you can put that number on either vector. Put it on u and then do the dot product, or put it on v and then do the dot product, but not both. Right? You got to do one or the other. And you'll get the same result all 3 times. Right, so it's basically saying you can kind of just move scalars around wherever you wish when you have a dot product multiplied by a scalar. All right. Now this is just fill in the blanks, what properties are being used. So for instance, if I want to show, that c, some scalar c times the dot product of u and v is equivalent to u dot, c times v. Notice the first line here is c times u dot v is, c times, and then this quantity u1 v1 plus u2 v2 plus blah blah blah. This is just how the dot product is defined. All right, so the first line there is the definition of the dot product, the algebraic definition of the dot product. Right, so I put that in part A there. Right. And then the next thing, see, I got this scalar c times this big sum, and then it gets distributed, right? Now the c is on every single term. That's just a distributed property of real numbers over addition. And I'll let you fill in the last two. Okay. All right, so now the last part of this section is on things called projections. All right, we're going to be projecting one vector onto a line containing another vector. All right, that's projecting one vector onto a line containing another vector. All right, so the first of the projections, there's a scalar projection and a vector projection, but they're both related to the same kind of picture, and I'll draw you a picture in a second. So the dot product can be used to find the scalar projection of a vector onto another vector. The scalar projection of vector u onto vector v, denoted by, this is component, it's like scalar component, COMP, of u onto vector v. So the vector you are projecting onto is the little subscript here, and the vector that's getting projected is, I'll put in parentheses, it'll be like a function, is a scalar that gives the length of the component of u in the direction of v. Now let me show you where this little formula comes up. I'm going to draw you a picture of a projection of one vector onto another. Okay, so here's the start of my picture on vector projection. So say I wanted to project vector u, this purple vector, onto vector v. So what do? What you do is this. First you connect them, right? Make sure that they have the same initial point. Right? So I'll write that here. Notice they have the same initial point. Right. And I wish to project u onto v. So what you do is you go to the terminal point of u. Right? Where does vector u end? And then you draw a perpendicular segment to the line with v on it, right? To the line with the same direction as v. So I'll make this little dashed. Right? This is just drop it straight down so that we are perpendicular, right? Forming a right angle with vector v here, so that would be at this point. Now if vector v was pointing this way, we'd still drop straight down. Again, you're going to draw a perpendicular segment to the line with vector v on it. All right, now you see what I've just created now? A little right triangle. All right, there's a little right triangle here. And what I've just also created is kind of a new vector. All right. Let me put this with this color. So if I start at this initial point, and instead of going all the way to the end of v, I just go to the point that we dropped down to from the end of u. I just draw this vector here from this point to this point. All right. This vector I have just drawn, this is called the vector projection of u onto v, this vector here. Now, instead of writing all these words, all right, this vector projection is labeled this way. It's PROJ, right, like projection of vector u onto vector v, right? So the vector you are projecting onto is the subscript here, and then my vector in the parentheses is the one that got projected. All right. So this vector here is called the vector projection of u onto v. It's labeled this way. right? And then the length of this vector is that scalar projection that was being talked about on the previous page. Then the magnitude of this, right, the length of this projection vector this is called the scalar projection, right? Just how long that vector is. Well, I guess I shouldn't say that exactly. Because it can be, all right, so I'll say plus or minus, because it depends on which direction. If you're pointing in the same direction, if the vector projection points in the same direction as v, this scalar projection will be positive. If it points in the opposite direction of v, it'll be negative. So that's why I should I'll put a plus or minus in front of this, and this depends on the direction. It depends on direction. So this is called the scalar projection of vector u onto vector v, which was given by that component COMP of u onto v. Lots of notation again. Hopefully this is gonna be a lot of wording, a lot of lettering here. And I do apologize, but we'll get into some examples where I'll draw some similar pictures. All right. Well, now what I would like to do is figure out, what's, you see how this is pointing, this vector projection is pointing in the same direction as v here. So that means it's just a scalar multiple of v. Remember, when you multiply a vector by a scalar, it just makes it shorter or longer or pointing in the opposite direction if it's negative. That's why I got the plus or minus here. So we just want to figure out what scalar that's what this component thing is. What scalar do I multiply v by to get this new vector at the base of this right triangle, this projection vector? All right, so looking at this right triangle, we've got this angle here, this angle I'll call theta. Right, theta is the angle formed by u and v. All right, theta is the angle formed by u and v. And you got the lengths of these sides. Right? The length of this side, the length of this is the magnitude. Right? The length of this side is the magnitude of vector u. The length of this whole side is the magnitude of v. But then, the length of this thing here, right, the length, right, the length of that projection vector, the length of this base. To find that, I would need the cosine of theta, right? Remember, cosine is adjacent over hypotenuse. So it'd be this length, the length of the projection vector, divided by the length of the hypotenuse, the magnitude of u. So it'd be, if I solve for the projection vector, it'd be the magnitude of u times the cosine of the angle between u and v. All right, again, using this right triangle, I can solve for the length of this brown vector. And then what I do next is I'm going to multiply the top and bottom here by the magnitude of v. So I have magnitude of u times magnitude of v times cosine theta divided by the magnitude of v. And hopefully, just again multiplying this by in the numerator and denominator by the magnitude of v, and hopefully this numerator looks familiar. When I multiply two magnitudes by the cosine of the angle between them, that's the dot product. So this is u dot v in the numerator divided by the magnitude of vector v. And this is this scalar projection of u onto v. This is the scalar I need to multiply v by. Well, this is like kind of the length of this, right? So now I would like to find a formula for this vector itself, right? You know, what are the components of this vector? So we need a unit vector in the length in the direction of v. Same picture up. Now this is also something that hopefully is familiar to you. A unit vector in the direction of v would be the following: just 1 divided by the norm of v times vector v. Remember that? That was normalizing. That was in the last section. So that'll give me a unit vector in the same direction as v. And then to make it into the Brown vector, you know, if this has length 1 unit and I want to have this length, I just multiply the unit vector by that. Right? This has length 1 unit. If I multiply it by this scalar here, it'll have that length. So putting all this together, again, lots of crap here, lots of letters. Hopefully, maybe it doesn't make a lot of sense, but we'll get to an example with some numbers. Maybe that'll make it a little clearer. So then the vector projection, right, that brown vector I had there, the projection vector of vector, you know, of vector u onto vector v, is this unit vector multiplied by this vector here. Well, if I multiply these, you know, you see how the denominators both have the norm of v. So that's u dot v divided by the norm of v squared, right, because they both got the norm of v in the denominator, times vector v, right? So there's a scalar there times vector v. Right, so you got a couple formulas here. Right. Again, this component, this scalar projection, is a number, right? That's why it's called the scalar projection. This guy here is just a number. Basically kind of gives you the length of this, and it gives you the length and also tells you what direction it's pointing in. You know, if it's positive, it points in the same direction as v. If it ends up being negative, it's pointing in the opposite direction. That's why I put this plus or minus here. And then this is the actual vector itself, right? The actual projection vector. Okay. Now another way you could also express this formula, when you have the norm, the magnitude of v squared, that would just get rid of the square root, and you'd have basically v dot v, you know, the v dot itself, as you have the sum of the squares of the components, each component multiplied by itself. So another way to express this projection vector of u onto v is u dot v divided by v dot v times vector v. Notice how many times the vector that you're projecting on shows up. You know, vector v is all over the place. The vector that you're actually projecting, once. All right, so let's look at an actual example with numbers. All right, again, there's a lot of letters, a lot of jargon here. I'm going to draw, again, a similar picture with some actual numbers. And here we go. Okay, so here are the vectors given in the participation activity right after they introduce projections. Got vector u is components 5, 7. All right, this is an R2 here. Vector v is components 8, 4, so 8 to the right, 4 up. So I've drawn those here. And I'm going to project vector u onto vector v, or at least the line with vector v on it. So again, the way that's done is this. I make sure they're both in standard position here. They're both starting from the same initial point. If I'm projecting u onto v, I go to the end of vector u, the terminal point of vector u, and I draw a segment that's perpendicular to the line with vector v on it. And I'll make this dashed. And make it perpendicular, right, 90-degree angle there, to the line with vector v on it, and that would be at this point here. Okay. And that kind of creates a new vector that's pointing, in this case it would be pointing in the same direction as v. So you're going to see the scalar projection will be positive. If the scalar projection is negative, you'll get something that points in the opposite direction. So here's the vector projection right here. There's the projection, PROJ, of vector u onto vector v. Right. The projection of vector u onto vector v. That's this vector I just drew here, ending at this point that's directly beneath the end of vector u, going straight down to vector v, perpendicular to vector v. Okay. And then as I drew in my previous picture, right, vectors u and v right, have some angle between them. Right, the angle between them is this theta. And the length of this vector is the norm of the magnitude of u. Now we know what that is, right? The magnitude of u. Well, I don't need to find it, because what we're going to see is here now, like, look at this, right? The length of that projection vector, the length of this brown vector here, this side of the right triangle, right? You see the right triangle here? The length of this projection vector, right, the projection of vector u onto vector v, is going to be, the norm of u times the cosine of the angle between them, right? Because again, remember, cosine's adjacent over hypotenuse, and I know the hypotenuse, it is multiply by the hypotenuse to get the adjacent side. This projection vector is the adjacent side to that length. And then, as I said before, you take this little guy here, the norm of u times cosine theta. I multiply the numerator and denominator by the norm of v. So it's norm of u times norm of v cosine theta divided by the norm of v, and I get that same formula I got earlier. This is u dot v in the numerator divided by the norm of v. And again, this is called the scalar projection, or component of u onto vector v, or the component of the projection of u onto v. That's what this little formula is, right? So let's find that. Let's find the scalar projection. I'll do that off to the side here. So the scalar projection, again, this component of the projection of u onto v is, u dot v. So the numerator is u dot v. What's u dot v? That'd be 40 plus 28, that's 68, divided by the norm of v. Now, what's the norm of v? That'd be the square root of 64 plus 16. So the square root of 80. And we can punch this in, and I'll get an approximation. Pull the calculator up. So I'll take, we got 68, the dot product of u and v in the numerator, divided by the norm of v, right, the square root of 64 plus 16, square root of 80, in the denominator. And this is approximately 7.6, right? So this length right here, this length is approximately 7.6 units long. Right? This vector that I drew from the origin to this point directly below u onto v. All right. So that's scalar projection. And again, because this ended up being positive, means that our vector here is pointing, and you can see it in the picture, is pointing in the same direction as v. If this ever ends up being negative, again, all that means is that our projection is pointing in the opposite direction of the vector we're projecting onto, the vector v. All right, and then I mentioned vector projection. Right? So then the vector projection, what is this vector? That's this PROJ projection of u onto v, and I had that formula here. All right, this was this scalar. It's just basically it's this component multiplied by the unit vector in the same direction as v. If you take the unit vector in the direction of v and multiply by this component, this scalar projection, you get the vector that this brown vector that I've drawn here, the components of this brown vector. All right, so you can think of it as u dot v divided by the norm of v squared, then times vector v, or u dot v divided by v dot v times vector v. I'll write that up, right? I like that formula with the two dot products. U dot v divided by v dot v times vector v. All right, so what is that? Now u dot v we saw was 68. V dot v is 80. All right, it's just the norm of v squared times vector v times the vector 8, 4. All right. Now, 68 80ths reduces a bit, but I'm going to do this, putting this scalar into the vector v, 8 goes into 80 10 times, so 68 divided by 10 is 6.8. And then 4 goes into 80 20 times, right? So that's 3.4. 2 goes into 68 34 times. That'd be the same as 34 tenths, 3.4. Right. So this is these are the components of this brown vector. So this point here, this point was 5, 7. This point was 8, 4. This point here, from the origin out, this vector projection, this is the point 6.8, comma 3.4. It's 6.8 units right and 3.4 units up. Right. Yeah. But yeah, so again, hopefully the numbers made this a little easier. I'm going to do it again. Right? I'm going to do it again with another example, but that's what's going on here. Right? Projecting one vector onto another. Again, they show you that the length of this projection is about 7.6, as I had earlier, right? The dot product of u and v divided by the norm of v. And then we get into vector projections, right? See, now I showed you this formula already. U dot v divided by the norm of v, or the magnitude of v squared, which is the same as v dot v. Right? You could say v dot v is the magnitude of v squared, and then times vector v. And they give me an example here as well. So I want to actually just go back here and do another one like this. Right? So I want to do several of these. This is I know the first time people see this, they have a hard time. Right? Maybe because I don't explain it very well, but maybe if I do more examples, it'll help. Right, so again here, I'm given vector u as -2, 1. There's vector u. Vector v is -3, 0. And we're asked again to find the scalar projection. That's this component of vector u projected onto vector v. And again, the formula is u dot v divided by the norm, or the magnitude of the vector you're projecting onto, right? This subscript here, divided by the magnitude of vector v. All right. Now, drawing a picture of this, if I'm projecting vector u onto vector v, it means I go to the end of vector u, this point -2, 1 here, and I just draw a perpendicular segment right there, right, creating this little tiny, it's tiny on my screen here, a little right triangle. And then this vector right here, from here to here, here to here. Trying to make it thick. This vector from the origin pointing, again in the direction of vector v here to the point right underneath vector u that I projected downward. This is the projection vector. This is that PROJ of vector u onto vector v, and hopefully it's easy to see in this picture. This is the vector -2, 0. Right? It's just 2 left, 0 up. And its length is 2. And it's pointing in the same direction as v, so this component will be positive, you'll see. All right, and let's check that out. Let's go through the formula. So what's the numerator here? U dot v, 6 plus 0, divided by the norm of v is 3, right? The square root of 9. And 6 divided by 3 is positive 2, as I said, right? This has now again, this is positive, meaning that the projection vector is pointing in the same direction as vector v. Right? It's pointing in the same direction. Yeah, so 2 is the scalar projection. And then what is this vector? Right? What's the vector projection? Just what is the actual vector that I've drawn here? Again, that's this PROJ, projection of vector u onto vector v. Again, the easy formula is just u dot v divided by the magnitude of v squared, or v dot v, times v. So this is 6 divided by 9. Right. U dot v is 6, v dot v would be 9, times vector v times -3, 0. 6/9 is 2/3. 2/3 times -3, 0 would be -2, 0. Right, so this vector I've drawn here is the vector -2, 0, with components -2, 0. Right, and obviously it has a length of 2 units. Right. So back here, right, all they want is the scalar projection, right? Just that u dot v divided by the magnitude of v. So that was just 2 here. Okay. Now you could do this one. Now again, it doesn't matter if you're an R2, R3, R5. It's the same formulas. All right, so this is A onto B, right? So I'll just write this out. I'm not going to draw it because my drawings in 3 dimensions aren't the greatest. But I will do it on paper, find the scalar projection and vector projection just to practice that as well. Okay, so first let's find the scalar projection, right, which is basically just kind of like the length of the projection vector, and we're doing A onto B, right? We're projecting A onto vector B here. You could do the other way around too, but just switch everything, that's all. So the scalar projection, again, is the length of that projection vector, and if it's positive, it means the projection vector is pointing in the same direction as B, and if it's negative, it just means the projection vector is pointing in the opposite direction of B. So we're doing this as that component of vector A projected onto vector B here, and that's A dot B in the numerator divided by the magnitude of B, right? The magnitude of the vector you're projecting onto in the denominator. A dot B, 3 components, right? So it'd be 2 plus 0 minus 12, so -10. Right? 2 plus 0 minus 12. -10 in the numerator, and then the norm or magnitude of B be the square root of 1 plus 25 plus 9. This is square root of 35. Right? And they want us to round to 2 decimal places. Right? So on my calculator, pull up -10. Now notice it's negative. Again, negative means that the projection vector, and I'll write this down. I know I've said it, but this end up being a negative number, this scalar projection. All that means is that the vector projection, the projection of vector A onto vector B, the projection vector, is in the opposite direction of B, of the vector we're projecting onto. Is in opposite direction of vector B. That's all that means, the fact that it's negative. Divided by the square root of 35. That's approximately -1 1.69 if I go to 2 decimal places like they're asking me. Okay, so the length of the projection vector would be 1.69 units long, just again in the opposite direction of vector B. And then the vector projection itself, what is that projection vector? That's this PROJ of projection of vector A onto vector B. Again, the formula would be A dot B in the numerator divided by the magnitude of B squared, or B dot B in the denominator, and then times vector B, right? Again, the vector you're projecting onto, this subscript is showing up all over the place. So the scalar here would be negative 10 divided by 35, right? The square root of 35 squared, times vector B, and vector B has components negative 153, and we get the components of the projection vector. Now negative 10/35, it's 2/7, right? 2/7. So we get positive 2/7 for the first component, and 10/7, negative 10/7 for the second component, and negative 2/7 times 3, negative 6/7 for the third component. These would be the components of that projection vector. Again, if I drew a picture, drew a little right triangle, the base of that right triangle, that vector would be these components here. All right, it's just those 3 dimensions, and I didn't feel like drawing all that up because it'd be crap. But yeah, all they asked for again was the scalar projection, right? That A dot B divided by the magnitude of B, and they see a type as number, point, number. So round to the nearest hundredth, negative 1.69. And they draw a little picture. So see they give you a better picture here. Here's A, B's pointing off this way. And when I draw the projection of A onto B, notice it doesn't go onto B, it goes on the line containing B. But I do still draw from the end of A perpendicular to this line that has B on it. And you see how this projection vector from this point here to this point is pointing in the opposite direction of B, and would have a length of 1.69. Alright, now you can do the same thing with 5 components. It doesn't matter. Right? So when they want the scalar projection here, just it's m onto n. So the scalar projection, that component, would be m dot n divided by the norm of n. Right? But they just have 5 components now, no big deal. And I've already told you about the vector projection. You're just actually giving the vector, right? Like here, what would be this vector? And I showed you those components on the previous one. All right, so I'll do another example. You can watch the animation. I'll just do this example here. Now you see the vector projection. Notice the answers are vectors, right? They're giving you some components and asking you for the missing one. And then the challenge activity puts it all together. Alright, so I'll do this here, just one of these examples. But again, I like doing the 2-dimensional ones because they're easier to draw. And you could try drawing the 3-dimensional ones. This one's 5-dimensional. Not going to draw that. But yeah, I'll just do the first example on paper here. Okay, so here I have vector u is 3, 5. Vector v is 2, negative 1. We're projecting u onto v. Now the dot product is not 0, right? It would be 6 minus 5 is 1. Now, and my drawing looks like these are 90 degrees, but this is not 90 degrees. I'd go from the end of u, draw a perpendicular segment to vector v, right, like this. This is terrible. I'm going to create this little right triangle, which is, again, pretty awful. But this vector here, then, from here to here, very tiny vector. This little guy right here, from here to here, that's the projection vector. That's the vector projection, the projection of vector u onto vector v. So I'm expecting some kind of tiny components here. It looks like both components are less than 1, right? This is 1 unit right, this is 1 unit down. It looks like both, just based on this, it's kind of a crappy drawing, but based on this drawing, looks like my projection vector has components, less than 1 and less than 1, right? 1 unit right and 1 unit down. All right. Well, we'll see. Now they're only asking for the vector projection. What are the components of this vector? And I'll write that here, vector projection. So we're doing the projection of u onto v. Again, the little formula was u dot v divided by v dot v, or the magnitude of v squared, and then times v. All right, so I mentioned u dot v is 1, 6 minus 5, u dot v. Then v dot v would be 2 squared plus negative 1 squared. 2 times 2 plus negative 1 times negative 1. V dot v, or the magnitude of v squared. This is 5. Right. So the square root of 5 squared. 5. And then times v is 2, negative 1. And there we go. 2 fifths, or 0.4 for the first component. Negative 1 fifth, negative 0.2 for the second component. So that's this here. See, this is going to the right 0.4 and then down 0.2. Right? That's this little vector right there. Has components 0.4, negative 0.2. And they've already put in the 0.4, so I'm putting negative 0.2 for the second component. And again, very easy, just, same formula, just different letters. Make sure you know what vector you're projecting onto, and you can do it for 3 dimensions or 5 dimensions here. All right, then the challenge activity, you just have to pay attention to whether they're asking for the scalar projection, right? Just or the vector projection. Do they want to? If they ask for this comp, right, component, that's the scalar projection. Your answer should be a scalar. And for a vector projection, that's the proj, right? That's this thing here, the that's vector projection. Your answer will be a vector. So if I start this. This first one, they want the scalar projection, right, component of the vector of u onto v. So this would be u dot v, and I'll pull a calculator up and do this. So the numerator of this, remember, is u dot v. So 24 plus 3, that's 27 in the numerator, divided by the magnitude of v, right? See, the subscript here is v. The vector you're projecting on is v. That'd be the square root of 17, the magnitude of v. So the square root of 17. And then notice how they want us to round to the nearest thousandth, right? In the example, it's 1.234, 3 decimal places. So 6.548, and then that would stay an 8 because the next digit's a 4. So I would round down to 0.548, 6.548. Okay, and again, they're going to probably... Again, some of these will be, all right, so this is another, find the scalar projection, and I'm assuming that the last two are vector projections. Yes. All right, see how number 3 here is a vector projection. You see I got 2 components. So that's the u onto v. So I have u dot v divided by v dot v, and then that scalar times v. All right, times the vector 2, negative 7, and you get your components here, again, rounding to 3 decimal places. So I'll leave those to you. All right, then you have your additional exercises. Again, some of these are on assignment 5, some are not. I still would recommend doing all of them just for extra practice, extra exposure to the material. And you can view the solutions if you want to check how you're doing, but only use them to check how you're doing. Please try to work on the problems and work them out and figure them out before you look at the solutions. All right, because you're not going to learn anything if you're just looking at the solutions and copying them. Right. And that'll make exams that much rougher. All right, so that's it for chapter 3, really. See at the bottom here, we're going into chapter 4 on things called determinants of matrices. This is it for the introduction to vectors and some operations on vectors. We'll spend lots of time talking about vectors in later chapters. All right, so thanks for watching. Again, if you have any questions, let me know, and have fun with section 3.3 here.